I think we could wait a couple more minutes. I'm sure more people will join.
Okay, then 2 more minutes. Okay, let me share the screen. So do you see my screen?
Yes.
Okay, excellent. Okay, I think we start, Christo, and whoever joins later.
Yes, let's kick off.
So you made the introductions. So I know almost everybody. So for those who do not know me, I am Kyriakos Hagiannagou. I am a research scientist at the Cyprus Institute. And in this session, I will concentrate more on how we can use GPUs for our applications. So first of all, I would like to know if you have used in the past GPUs, okay, and for which reason, if any of you used. So none of you use GPUs, okay. I assume some of you maybe you have used GPUs for video games, but okay, now we will focus on how we can use GPUs for other things, for what we call for general purpose, and this is where this term Computer Unified Device Architecture is introduced in order to allow us to use the graphics processing units for general purpose. Because as you probably know, as their name suggests, that architecture has been introduced with the idea that you will do graphics. So in graphics, we are doing it for video games a lot. This is why this kind of technology has been developed, because the game industry, as you know, is huge, and this was motivated further development in the GPUs. Okay. So, okay, we'll have one more participant joining. So before we have the opportunity to be able to use GPUs for general purpose, one has to use complicated library like OpenGL in order to be able to communicate with the GPU. And of course, this was not user-friendly in the sense that one can use the power of that compute unit to do other things. And in 2006, it's been already many years, NVIDIA, I will concentrate mostly on those kind of GPUs. There are also other names, big names in the market that are producing GPUs like AMD, but mostly I will concentrate in the case of NVIDIA. Okay, so NVIDIA was the first one who tried to make an attempt to introduce a platform that the user can use GPUs for other things. Okay, so CUDA has been introduced in 2006, and the goal is to be able to use all this parallel nature of the GPU in order to accelerate calculations. And one thing that sorry, yeah, and one thing that that GPUs allow us is to take a CPU code, then do some modifications, as I will show later, and then this will be able to run on the GPU. Okay, but of course the GPU is not able to use operating system directly. So I will say more details about it. Okay, and CUDA, when it has been introduced, it was you were be able to use it through C. Okay, there is also a CUDA for Fortran, but since C, C++ is more common, I will concentrate on this case. Okay, so when one uses CUDA for C, C++, it provides extensions on the standard C, C++ language that we know. And the extension that it provides allow us to do a heterogeneous computing. So this is a terminology that we use when we have different kind of compute units that co-work together to complete a calculation. Okay, and CUDA, one thing that it provides, it provides the API. Okay, and through this API, we can communicate some things with the GPU, and it provides also some special kind of instruction to instruct the GPU directly how to do calculations. I will show, as I said, many examples later. Okay, so this figure that I show here is to motivate a bit why we need to reconsider of replacing the standard CPU servers that we have with more compute capable nodes that are equipped with GPUs. Okay. So in this case, this figure I took it from NVIDIA's website, and it tells you the following. Let's say that I give you, okay, one GPU node. I will show a bit later how a GPU node looks like. And the GPU is equipped with 4 GPUs. And let's take the example that these are a specific architecture that we call Volta. So with this one GPU node that has 4 GPU, depending of course on the field, because different fields may be more suitable for using GPUs, how many CPUs you replace? Okay, and when we compare with CPUs, we are talking about some dual core CPUs. And in this case, in an application related to life science, can replace up to 14 CPU nodes. In other applications from physics, it can replace 70 or 32, and one from geoscience, it can replace up to 54 CPU nodes with one GPU node with 4 GPUs. So this is a dramatic improvement. So this is the main reason why more and more supercomputers around the world are going in the direction to have GPUs, because are more capable of doing fast calculations and are more energy efficient in the sense that they do not consume as much electricity as the CPU meaning how many calculations they do per watt, for instance, that they consume. Okay, so now what we will learn today? So today I will go to several examples how we can write small CUDA kernels. Okay, I will discuss how we can exchange information between a CPU, which is what we call central processing unit, and the GPU, and the other way around, of course, and how we can synchronize those two different devices, because since now we have two different devices, we need to do some kind of synchronization. And if we are interested for performance, it is always good to know how much time you need to execute something. Okay, because for some applications, it's important that things happen fast. And I would go also to some details how one can distribute the compute. Okay, so of course more will come later. Now, what prerequisite you need in order to follow closely this? So you need to be familiar with C, C++. Okay, familiar. You don't need to be an expert, of course. So if you can please raise your hands, how many of you are familiar with C, C++? Okay, I took 2 hands, 3. Okay, not so many. So the rest, what you are familiar with, if you can write me. So I think you can write me in the chat. Okay, Python, I will have examples later with Python. R, oh, yeah, R sounds like a statistician. Yeah, R. Yeah, okay. Okay, but in any case, the example that I will show, they do not have difficult things in C that someone cannot understand. So if one has a basic understanding of coding, it's easy to follow. Okay, later I will show some examples with Python. Yeah, I don't expect you to have experience with graphic cards, even if it's an advantage. I will explain you the ideas how it work. Of course, it's good always to have a basic understanding what is the meaning of parallel programming. And then I will go to show how we can use Cyclone and some libraries in order to do the calculation distributed. Okay, so CUDA comes with several concepts that we will discuss in this session. So it first has the concept of heterogeneous computing, because you have the central processing unit that is responsible for the main operations that need to be taken for an operating system to function. Okay, and then you have, let's say, a booster. This is how one can describe a GPU. And booster for the calculations that you can offload, okay, the most computation and demanding part to this booster. Okay, then we will go to concept about what are the CUDA threads and what are the CUDA blocks, how we can index the threads in order to get the unique index to do the calculation. how to do synchronization, how to use advanced memory structures like the shared memory, the device memory, I mean the memory on the device, how to do asynchronous operation, how to handle errors, and many more concepts that I will discuss later. Okay, but let's first introduce the terminology that is mostly used in this kind of heterogeneous computing. So on one hand, we have the CPU, and as its name says, it's a central processing unit. So this is, let's say, the head of the coordinating the calculation, and we call it host. Okay, so from now on, we'll call the CPU host of the calculation. And the CPUs, as you know, they come with memory. Okay, and the CPU memory now, obviously, we'll call host memory. On the other hand, we have the GPU, a graphic processing unit, that we will call it device. So this is the terminology that is used. And of course, the GPUs come with their own memory. Okay, and usually the memory of the GPU is much more limited, much smaller compared to the CPU. Okay, in the specific example, I show an NVIDIA card, which is the Volt architecture that is specialized for high performance computing. Okay, and now let me show you how one node looks like. So when you have a supercomputer, this supercomputer has several nodes. So you can imagine a node of each node of that supercomputer to be like this. Okay, so let me describe it a bit so you can understand. So this node equips the fastest supercomputer in the United States, which is called Summit. I will discuss that machine a bit later. Okay, so what we see here is that this thing that you see here and this are the CPUs, are the central processing units. So you see two are located on this node. Okay, and those things that are above the CPU that you see them covered, you cannot see really this thing, is for cooling. Okay, they have this tube that they are cooling the CPUs. And you have the RAMs, the RAM for the CPU, those things that you see here. So you can take them off and replace them, and you can put larger memory if you want for the CPUs. And then we have what you see here. You see 1, 2, 3, plus 3, 6. So what you see here are GPUs, but are not like this one in the sense that they do not have this cover above that you see here. Okay, and they do not have any ports. Also, this one does not have any port, and the reason that they does not have port is because it's specialized for high performance computing. So you cannot use that one to visualize. So the standard GPUs, they have ports here that you can connect to the monitor. Those one, they do not even have the cover to have less space. And their GPU memory is under this cooling system that you see here, because it's very important to cool to keep those computational units under cooling, because they consume a lot of electricity and they warm up very fast. So this is why they have sophisticated cooling system. And of course, you have the power supply here. The motherboard is underneath. Okay. Now, let's see how how a hybrid code looks like. So as I said, we will do a heterogeneous computing. So we want to come with an idea how we can use both these different architectures. The head, what I say, is the host of the calculation, and the smart part here, the smart device here, and how we can make them collaborate. So when the usual structure of a hybrid code that we need to write, it starts like this. So the CPU will start with loading some parameters or initialize the program, read on the CPU the executable that we want to execute, and it provides the instruction about the calculation. And we start with one thread. Okay, what you see here is one thread. So a thread is a piece of instruction, okay, let's say fundamental piece of instruction that will be executed on the cores of this central processing unit. Okay, and then when you do the initialization, as I said, you read the data. You may need to transfer those data from the host to the device, okay? Because the device memory, it's much closer to the GPU, and it can fetch information much faster if it's on the GPU. By the way, anytime that you have question, please either raise your hand or unmute your microphone and let me know. Okay, so don't hesitate to interrupt me anytime. Where I was, yes. And the next step is that after you transfer those data, you want to tell to the GPU to start doing the calculation. And of course, as I said, the CPU, which is the host of the calculation, and it informs the GPU to start doing the calculation. So the GPU creates a lot of threads, okay? Because it has so many cores, it has thousands of cores, and it can process the calculation in parallel. So this is exactly the idea why this is working, because let's say that you have to do the same kind of calculation on different elements of a data set, but you need to do the same. So you want to have workers, let's call these thread workers, let's say, and you want those workers to work on the same time with the same instructions usually, okay, but on different elements. And then if they work in parallel, then the work can be done much faster. Okay, so let's take the example, as I said, that we have some builders that are building your house. So you can have several builders simultaneously working on different parts of the house. Some of them can do same things, some of them can do a bit different things, and then you can finish the house much faster. But the speed that the worker works is finite. Okay, you cannot make a worker work much faster than an upper limit. So what you usually do is that, okay, I accept that there is this limit, but I can increase the number of workers that I can have. So there is a limit of how fast one builder can build your house. Even if you get the faster in the world, okay, there is a certain limit, but you can get many, many of them. And the only drawback to get many is the overhead, of course. The overhead is that they need to communicate. The builders who have to say the other one, so they need to exchange some information to coordinate. So it's the same thing, exactly the same thing with the GPU. So the GPU, imagine that it has several execution units inside that they can, on the same time, do the follow the same instructions, how to perform, but on different data. Okay, and I will discuss more about it later. It's not, however, as fast as the CPUs are, in the sense that we have a CPU core that usually now vary, I mean, the speed between 3 to 4 gigahertz, but you cannot really make them more fast. So some attempts to make them more faster, the CPUs, because of the limitation of making the transistor smaller and smaller to increase that speed, they get problems with heating. So the maximum we have achieved regarding the speed of a core, it was 7-8 gigahertz, if I remember correctly. But they lived only for a very short period of time because such fast CPUs burn very fast and die. Okay, so since we have this barrier that we cannot do the cores much faster, we put more. Okay, so now the device will do in parallel this kind of intensive calculation, and then when it's finished, yeah, I forgot to mention that when the host tells to the GPU, okay, this is the work that you have to do, go ahead and do it, the CPU can do other small things. Okay, so it has sent the instruction to the GPU. We can do some other more small calculations if it's needed. And when the GPU is completed, it reports to the CPU or host. We finish. Now you can get my data back if you want to visualize it or if you want to continue another kind of calculation. So this is the general structure that the hybrid CPU-GPU code has. Okay, and now I would like to tell you more things about the differences, so you understand deeply why we cannot use this thing for a very heavy parallel calculation. Okay, one issue that it has low computational density, in the sense that those things come with a limited amount of cores, 10, 20, maybe have up to 32. The GPU is a high computational density, so it has many of them. When I say many, I mean of the order of 5,000. Okay, but on the other hand, the CPU ones, they have a very complex control unit. As I said, they should be capable of handling operating system. Okay, so if they're capable of doing things like this, they should be smarter. Each core, let's say, it's smart. Now this thing is high throughput on the other hand, in the sense that it can access data. By the way, I forgot to open the camera. Maybe this is better. So so that they can fetch data from the device much faster. And this is very important because they have so many workers waiting, so they are capable of getting data very fast. Now, I think that a CPU is good, is that they have a large caches. So they can do a lot of caching in order to, when they have data that are used very frequently, to put them in those caches so they can access them fast enough. So they have L1, L2, L3, and actually the 2, 3, they are of the order of megabytes, so they have very good caches. Now, on the other hand, the GPU has also, but it's not so big. Okay, the register now on the GPU is what is big. So the registers are the closest storage units on the either a CPU or GPU. Okay, and those registers is just the the step before taking the data and give it to the compute units to do the calculation. So this is very, very fast. And this the CPU have a lot of RAM. So they have, now we have nodes that they have of the order of terabytes of RAM. So those are very fat nodes, as we call them. But usually they have 128, 256 gigabytes. I mean the high performance computing nodes. On your laptop, you may have 16 gigabytes, 32, in the best case scenario. And the GPU, now one thing that is not very good is that they have relatively small amount of RAM. So for instance, now the latest one that we have, the latest architecture, they can have up to 40 gigabytes. That in many cases, 40 gigabytes are not enough, in the sense that if you have very big data sets, that this is, it's becoming very common nowadays to have very big data set. You cannot fit those data sets in just 40 gigabytes. Okay, and a last important thing is that the GPUs has relatively simple control units. Let's say they have so many cores to work on a GPU, let's say many workers, but they are not so smart. They are not so fast, but there are so many. Okay, so in this sense, we can take advantage of these compute architectures. Okay, just a bit of a history about the GPUs that have been produced for high performance computing. So before 2008, I mean before the introduction of graphic cards for high performance computing, the GPUs were, as we said, produced for the game industry mostly, and maybe for your computer to do some kind of visualization. And with the introduction of CUDA later, Computational Center found out that yes, now we can use it for other reasons, like we can use them for doing physics, for doing chemistry, for doing engineering, and they produce more specialized cards for high performance computing. So the first one has the name Tesla, the architecture. Tesla, and it was in the family Tesla again, for some reason. So Tesla, the family, is related to those cards that they produce for high performance computing. Okay, and then in 2010, we had the Fermi architecture that again was in the family of the Tesla. And you see every 2 years, NVIDIA was releasing new architecture. So new architecture comes with new feature, new capabilities, etc. And here it shows on the y-axis a performance of some kind of calculation involving matrix multiplication, the performance per watt. Because usually you care about the performance, but also how much electricity you need to reach such performance. Okay, because in the end of the day, you need to take this into account. And usually those GPUs need a lot of energy, so they can go up to 300, 400 watts, which is a lot. And imagine to have many GPUs, you need megawatt to operate a supercomputer. Okay, and then in 2016 we have the Pascal, and in 2018 we have Volta. Volta is the architecture that we have on the supercomputer that we have here on the Cyprus Institute, and we will work on it a bit later. And the last summer, actually, NVIDIA released the newest architecture, the latest one, which is a pair. So as you can see, NVIDIA chose to give names to the architecture based on famous physicists usually. So they have a good taste. And yes, this is a very, I mean, also Volta are very good also for machine learning calculations. So they make them some specialization because machine learning, as you know, is a hot topic now. So they can do some kind of calculations that are related to machine learning relatively fast. Okay. Now I will go to more details about what we can find inside the GPU. Okay, so to understand it better. And in this case, I compare the successor and predecessor in the sense that I discuss the Volta architecture and the Ampere architecture. So one thing that, so if we take a CPU, the central processing unit, you know that it has many cores. So like a CPU has many cores, and GPU has what we call streaming multiprocessor. So let's say that this card by its own has many processor inside. Okay, so it's a big processor outside, and inside you have other processors. And in the case of Volta, this has 80 streaming multiprocessors. Okay, and in Ampere it has increased a bit to 100 a day. Okay, and each of these streaming multiprocessor, they have what we call CUDA cores. Again, the CUDA cores are not as strong as the CPU cores. They are, you cannot compare them one to one. They are not so powerful, but as you can see, they have many per streaming multiprocessor. So if you now multiply the two, I mean how many stream multiprocessors we have and how many stream multiprocessors we have, how many cores we have per stream multiprocessor, we have over the 5,000 for the Volta, and this has increased to 7,000 for the Ampere. Okay, and this, you can see here the difference between the two. One says floating point 32, the other says floating point 64. Okay, so for single precision, the 32, we call it single precision. As you can see, this has about, it has 2 times more single precision than double precision. This is inherited by the fact that the CPUs in the past mostly were doing graphics. And because they were doing graphics, it was not very important to do this in high precision. So you don't bother much if you do not have a very accurate value for 1 pixel. Okay, this will not cause big problems. But if you want to use those GPUs for general purpose, and I mean now talking about scientific computing, that there are fields that it's very important, the precision, and they need precision up to 64 bits, then you start considering to put more and more cores that are capable to do calculation in double precision. Okay, but still it's about the factor of 2 difference between single and double. So the clock speed, as you can see, this or the order of 1.5 gigahertz. So this is lower compared to the central processing unit. And the GPUs are capable to doing also calculation in half precision. Okay, so in half precision, it's 16 bits. So it's even smaller than a single precision. And they can do actually calculation very fast. So what we can see here, this unit that is related to performance. Okay, it tells you how many floating point operation it can do per second. So floating point operation, you can imagine you take a number and you multiply it by another number, or you add them. So this is one floating point operation. Okay, and for instance, if we care about double precision, you can see that Volta can do 8 teraflops. Okay, Ampere has increased to 10. Okay, and you can see that if you go to lower precision, you can do it. You can do more floating point operations. And the Tera, I hope you know what is it. So mega is 10 to the 6, beta is giga 10 to the 9, and then it is the next one, Tera 10 to the 12. Okay, so it's doing so many operations per second, one GPU. So imagine if you have many GPUs, I will tell later what numbers you can get about the performance. The bandwidth then, it's how fast it can move data from the device memory to the compute units. And typically this is measured in gigabytes per second, or if we exceed the 1000 gigabytes, we can talk about terabytes per second. So this exceeded this barrier, and now we have 1.5 terabytes per second bandwidth. The device memory, as I said, it's limited. So the Volta, they have either 16 or 32 gigabyte. I will show you a bit later on Cyclone how we can see this information. And now on Ampere, the latest architecture, it jumps up to 40 gigabyte. Okay. Now I described to you the streaming multiprocessors. So the streaming multiprocessors are, as I said, already very complicated architecture. So I would like to say a few things. How is their composition? So what kind of units they have? Okay, so we start with the instruction cache. So when you want to do some calculation and you need to provide some instruction on the computer architecture what to do. And this instruction usually, not usually, always comes from the, when you compile your software, compile it to some instruction and how this instruction pass to the compute units. And this instruction buffer holds this information about the instruction to be done, and this is a caching for the instruction. If some instructions are repeated, you can do some caching. Okay, and they have other specialized units. I will discuss later what a warp is, which let's say is a group of the threads that I will discuss later. And this scheduler schedule how these warps become active and inactive in the calculation. And the dispatch units are responsible of passing the data to the registers. The register, as I said, is the closest memory location to the execution unit. So before the calculation is done, and then we have the execution units that we have double precision units. What it writes here with cores are the single precision units. So as you can see, it has more green than yellow. As I said, more single precision units than double precision. It has also some units to do special kind of functions. And the most important ones are the trigonometric expression like the sine and cos. So there are dedicated compute units to do this kind of calculations. So one can really take advantage of those if you have trigonometric arithmetic to do. And we have also more complex things like texture, that this was, let's say, a legacy from the time that those units have been used for graphics. I will not discuss much about texture, it's not very relevant. And the shared memory. The shared memory, I will pay a lot of attention later. Okay, now from this now GPUs and CPUs, engineers or scientists around the world built very big supercomputers. Okay, and one example is the fastest supercomputer in the United States, which is called Summit. So Summit has a performance of about 150 petaflops. Okay, so this thing that you see here is equipped with 4,600 nodes. So you see those cabinets, and each one of them has many nodes. So you remember before I know you how one node of this Summit looks like. So imagine that you put them here in this cabinet. So you can fill many of them in one cabinet, and you have many cabinets. Okay, so each one of those nodes has 2 CPUs, and they have about ½ terabyte of RAM. And each node has 6 GPUs, as I showed you before, those 6 GPUs that they were on that node. And each one has 16 gigabyte of GPU. So it's the case of the worst architecture, they have 16 gigabyte. On the Cyclone, we have those that they have 32 gigabyte. We'll see later. And the electricity consumption of this machine is 13 megawatt. So you need to have, let's say, a small power plant next to the supercomputer to operate it. And these machines are usually built with government resources. There are cases that we have big companies that they have their own supercomputer, like ENI, the petroleum company. And those, they use them to do simulations for the extraction of oil and gas. Okay, and you can see how many millions you need to build such machines. Now, in Cyprus, we are a small country relative to the United States, so we do not expect that we have such a big supercomputer. So in our case, we have a much smaller one that we call Cyclone, and this has a peak performance about 0.6 petaflop. So remember, this has 150 petaflops. This has 0.6 petaflop. Okay, so if you take, if you want to understand, is it good enough? So you need to relate it to the population. So who can tell me what is more or less the population of the United States? So you can
million.
So about 340 million, that's correct. And in Cyprus, you know, it's about 800,000. Okay, so it's about, let's say, 300 times bigger. So it is not strange that we have something here which is about half petaflop, and they have 150. So for the size of Cyprus, this is a decent machine, let's say. Okay. Now Cyclone is equipped with 2 partitions. Okay. And now at this step, since we're discussing a bit Cyclone, I want to know if all of you have access to Cyclone. So please unmute your microphone and let me know if you have access to Cyclone, so we can discuss a bit how you can get familiar with the machine. So do you have access?
Yes.
I'm having a few issues connecting to Cyclone.
Okay, what issues?
I'm getting an error relating to authentication.
I think Minas can help you. with this kind of issues.
Okay.
Mina, can you hear us? He's in the meeting, but
I'm having the same problem too. Permission denied, says.
let me write to him. What about the rest? Do you have access?
Yes, I have.
Yes.
Me too. I just logged in.
Okay, I wrote to him, so hopefully he will help you to solve this this connection issue. But until then, I can go briefly show you how this this environment look like. So first, tell me, are you do you use? Have you ever used a Unix-based operating system? When I say Unix-based, I mean Linux or Mac.
Yeah.
Yeah.
Yes.
Okay, and get 3, 4 yes. Assume the rest usually are using Windows, which is common. So the supercomputers, just to know, all of them, I don't know, maybe there are some that are Windows, but almost all of them are Unix-based. So they have an operating system, which is usually Red Hat or CentOS. Okay, they're really more secure. So this is why I used like this. Okay, so, and those machines usually they have not graphical interface. Okay, so you can communicate fast by avoiding overheads for having this graphical interface to interact. And this, now what do you see here? Do you see the left panel of my presentation? So the left panel is a terminal that it will allow me to access to the machine. So do you see it?
Yes.
Okay. So this machine, as I said, has 2 parts. So if you go and write this as info, so if you open a terminal, or I don't know, in Windows they have, I don't know how it's called, PuTTY, something like this.
You can download Ubuntu for Windows as well, for anyone using that.
Yeah, okay. It's it allows you to install them through Windows. Yeah, and you can use them if you want. And so this is a terminal now that I have connected to this machine. So if you write host name, it replies to me what is the name of the node I am connected to. So they call it fraud 01. So it's a front end. Okay, we have one front end. So the front end is the node that you are connected to. Okay, is the coordinator, let's say, of the machine, is the head. Okay, and if you write the command sinfo, you are allowed to see the different partitions. So the partition that you see here, they say GPU and CPU, and the number of nodes for different status of those nodes. Okay, so as I said, we have 17 CPU nodes and 16 GPU nodes. What you see here with res means reserved. Those are reserved for this training event. Okay, and I will tell you more how you can use it a bit later. But for now, it was to get a bit familiar of what this machine looks like. And this is a Unix-based system. So you have the standard commands, like if you want to see your directories, you can do a list, which means a list, what I have in my directories. Okay, and we can discuss later the example. So if you want to follow the examples and be able to touch them and modify them, you need to be able to interact with this with the system, with the Cyclone. So tell me, up to now, raise your hand, how many have access to the machine and they can write commands? One. I see two more, three in total. Okay, we have four.
I can access the machine with the other account I have, but I don't. I can access with a account that was created for this event.
Okay, it's still fine. You may not be able to use this special reservation that we have put for this training event, but I think you still can. No, you still can. We will choose an account, and then you still can. You can still choose the name of the event and submit a job to that. Okay, so let me. Okay. Now. Okay, so each of these GPU nodes that it has 4 GPUs. Now, in my case, I am already on one of those nodes. Okay, which means I have allocated one of the nodes, and I have jump on it in the sense that I can directly interact with the node, and I will tell you how you can also do it in your case. So when you want to use one of those nodes or more, you have 2 ways to do it. You have the interactive way and the non-interactive way. On the interactive way, you directly give instructions to the node what to do. In the other one, you write a script, how the instructions how the instructions are supposed to be, and then you submit it. So you give it to what we call a queuing system to schedule when it runs, because there are also other users that they want to use the node simultaneously. So you need to the system needs to have a way to handle this. Okay, so in my case, I'm already on one of these nodes, and you can see here it tells which one it is. Okay, it's GPU 05. So it's the 6th, no, it's 6, it counts from 1. So it's the 5th GPU node. Okay, when I am on the GPU node, I can see, for instance, how many GPUs it has. I will tell you in a minute how you can jump on one node. I think we have reserved 4 of them, so we can do it one by one. Later we will submit scripts, so we will not have this problem. So when you are on a GPU node, you can write the command NVIDIA /SMI, okay, and it will reply to you how many GPUs it has. Okay, so as you can see here, it tells me some information. So you have 0, 1, 2, 3, so it means it has 4 GPUs. And it gives more information. So it gives, for instance, what temperature they have, how many energy they consume up to now, memory, and other things. Okay, so now let's see how we can interactively, for now, allocate those nodes so you can use them. So I exit. In order to be able to submit just under the reservation for the training, you need to be logged in with your training event account. Okay. But Mina, can you hear us? Hello?
Hi, yes, I can. Do you hear me?
Yes, so there are two people that they have some difficulties to connect with the machine. So if you can have a look and assist them so they can connect. But meanwhile, yes?
Just everyone who has issues, type the username in the chat so I can see who it is.
Okay, thanks, Mina. So please, those that they have issues, write in the chat what is the issue that you have.
So there are still two people who haven't sent any public key yet. So those will probably won't be able to access.
Not probably, for sure.
For sure, yeah.
Okay.
But just letting you know. But the others who submitted the key should be able to.
Yeah, okay. They will tell you their username, so.
Yeah, everyone should.
But okay, I have to continue.
Yeah,
so
okay.
For those that they have already managed to connect, now you can ask to allocate one GPU node with this command, for example. So let me put it in the chat. So
just a quick question before we move on. Sorry. Once you went into the directory and you connected with the SSH, you clicked ls to see the different files and directories that are there. Should we have other directories on our end or no?
Maybe the administrator create you one about the to store the data, but there is a possibility that you don't have one, but you can create if you want one.
Yeah. And the other one is just before this, the previous command you used was NVIDIA /SMI.
Yes.
That doesn't work for me, and I'm guessing it has something to do with the fact
that it's because you are on the front end.
Yeah.
And the front end does not have it because it does not have GPUs.
Okay.
So before you are able to execute it, we need to allocate a GPU node. Okay. And in order to do that, we use the command salloc. So this system has a queuing system that calls slurm. And with slurm, we can tell it that I want to do an interactive allocation with salloc. Okay, then we put how many nodes we have. We put this -n option and specify that one node. Okay. Yeah. And then we say that -p is the partition. As we say, we will use the GPU partition. Okay, this I will discuss later. So for now, you can just put it as I have put it. Those two I will discuss it later. Now the time, for how much time you want to make use of this machine. Then -- account is a special account that Minas created about the training event. So it's called edu30. Okay.
Yeah. Okay, thank you very much.
And then you need to put this -- reservation, because we did a reservation for this training. It was training event. So does it work for those?
Yeah, now after that it works. It just needed that. Thank you very much.
Okay, so let me see. Yes, I see two people that are in interactive mode. So, and maybe there are some that may need to wait because we have 4 nodes in total allocated for that. Yes, if we write as info, we can see, yeah, there are 2 more that they wait. However, I don't understand why this. Oh no, this one is a different one. So only 2 have managed to get access to this one, right? So one is Rafael and the other one is who? Who is the other one? Okay. In any case, so if you right now NVIDIA SimEA will tell you how many GPUs it has. Okay, so now if you want to stop, now we can exit that compute node, the GPU node. You just write the command exit. Okay, exit, and the presenter will exit it. So you will go back to the front end. Okay, now let's go to discuss the programming model that has been introduced from NVIDIA that allow us to use the GPUs for general purpose. Okay, so now we will come to the terminology. What are the CUDA blocks and what are the CUDA threads? Okay, so the first thing that we need to have in mind is that a CUDA block, it's an abstraction in the sense that physically, who is this person? Let me meet him. Hi, Ashley. Can you hear us? Hello? Okay.
What?
I just want to know if you could hear him.
Why?
Okay, anyway. And these CUDA blocks, they do not physically exist on the GPUs. It will allow us to pass information to the GPUs. Okay, and to be able to map the threads of instruction to the compute units of the GPUs. So a block, so what you see here is a grid. And grid is composed from blocks. And the blocks are composed from threads. Okay, so this is the hierarchy. We have the threads, we have the blocks, and we have the grids. And we have the grid can be 1-dimensional, 2-dimensional, or 3-dimensional. It depends on the needs of the user. So in this example here, you can see a 2-dimensional grid. And inside it, you see blocks. So the blocks, they have 2 coordinates, X and Y. Okay? And what I show here is that how a block looks like. So a block, again, can be 1, 2, or 3-dimensional. And inside the block, you can see the threads that they get indexed. So we can identify them. So again, they are X and Y. And you can see the index that they get. Okay, and those blocks, so for instance, here I show one block, are sent, someone is disconnected, and those blocks are sent for execution on the streaming multiprocessors. Okay, so, but there are limitations. So you cannot have as many blocks active simultaneously on one streaming multiprocessor. So there are some limits. Okay, and I will talk about this later. And there are also limitations in how those threads can communicate. So the threads can communicate with one block, but the different blocks that you may send for execution on a CPU, they cannot communicate it with them. The reason for that is that we need to allow up to a level for the schedulers on the GPU to do things in parallel. Okay, but of course not everything can be done without being able to communicate. So within the block, the threads can communicate, but different blocks cannot communicate between them. And different blocks can run on other streaming multiprocessor. Okay, but one block, you cannot split it into streaming multiprocessor. And the reason for that is, as we said, within the CUDA block, the threads need to communicate. And in order to communicate, they should be on the same streaming multiprocessor. Okay, and here on this illustration, I show the different kind of memory threads can access. For instance, they have access to registers. As I said, the registers are the closest, very close to the execution unit. And we have also the shared memory. So the shared memory, as its name says, is shared between the threads. So using that memory that is shared, they can communicate. And I will show examples later. And this shared memory is within the block. So within the block that the threads are allowed to communicate, this shared memory exists. And it's fast. It's not as fast as the register, but it's much faster compared to the device memory that you see here. Okay, so as you can see, there are no arrows between the blocks because the blocks cannot communicate directly, but they can communicate with the device memory, which is the slow memory here. Okay, now other thing that the GPUs have and is important to know is that they have what is called compute capability. And the reason that this capability exists is because GPUs have different features with newer generation, new feature introduced. So you need to be able to distinguish in which category each GPU is to take appropriate actions if you want to use that feature on the other feature, etc. For instance, the Volta is 7 and the Tesla is, the Volta is 7 and the Ampere is 8. Okay, now the threads that I described before that exist within the CUDA blocks, they are grouped in what we call warps. The warps, you can imagine it that it can execute simultaneously the same instructions. So each thread in that warp, it executes the same path of instructions. Okay, and the size of the warp is always 32. This has never changed since they introduced this CUDA framework. And the maximum size of those warps are per streaming multiprocessor is 64. So if you remember a few slides before here, I discussed that the streaming multiprocessor, they have a unit that is called warp scheduler. And this warp scheduler is schedule those warps, which are groups of threads, which one are active and inactive. Active, I mean, which ones are taking part of calculations, and which one are waiting for data to reach to register before they start doing executions. So the scheduler automatically, I mean, you don't really interact with the scheduler. I mean, behind the scenes, it decides which warps are becoming active or inactive in order to hide the latency of waiting for data. Okay, and as I said, they have 32 threads as a side, and only 64 are allowed for each stream multiprocess. Now there are more limitations in the sense that we cannot have as many threads as we want per block. Okay, so this is not max threads per stream multiprocess. This is max threads per block. Okay, so in total we can have 2048 per CUDA block. Okay, we have also the register that I say that there are some limits, how much register each thread will have. Okay, and the shared memory. So we said that since we want to communicate the threads within the block, we have this relatively fast shared memory. And it is of the order of 100 kilobytes, so it has increased from volta to ampere, but it's this order of magnitude. So it is limited, so one has to use it carefully. Okay, now we go finally to see how we can start writing some code for GPUs. But before doing that, we need to find a way to discriminate between functions that are supposed to run on the GPU than those that will have on the CPU, because we will do it in a hybrid, let's say, coding. So the system should know this information. Okay, and in order to compile a code, you will need, and this exists on Cyclone, the NVIDIA compiler. Okay, so if you see this screen now, my terminal screen, I will show you how you can load the modules which are which allow you to have access to the NVIDIA compiler. So if you are on the front end now, for instance, if you do module list, you can see what modules I have here. Okay, so you can see many listed here. And if we want to do it in an easy way, I will. I have a script that it will do it for you. But before that, okay, I have it later, so I will discuss it here. So let me tell you a few things now about the keyword that we need to put in the codes to distinguish between those run on GPU and CPU. And in the next slide, I will tell you how you can have access to the NVIDIA compiler. Okay, so the NVIDIA compiler can handle also a code that is written for CPUs. And it does not really compile that one. It has a host compiler, okay, and it passes the piece of code that is not supposed to be for the GPU to that compiler to be compiled. And the NVCC compiler deals with the GPU piece of the code, okay. And now I describe here what are the keywords that will allow us to distinguish between them. So if the keyword is it has this structure __ global __, then is the host who will call this, but it will execute on the device. So the host, when it starts the code, at some point it will call the GPU to do some calculation. So it will call it with this function. So the function that will be executed on the GPU as called by the host should have this keyword in front of it. Now there are also functions that a GPU will call, and this will have the keyword device. Okay, and there is also the case that the functions that the host will call will be executed on the host. Those they could have the keyword host, but this is the default case. So usually it's omitted. But if you have a function but you want to compile it for both architecture, both CPU and GPUs, you put both keywords, both host and device. So this is the case I have here. Okay, now we will see later that the functions that they have the keyword global, so those that we call from the host and execute on the device, they will take some kind of special arguments. Because before I discuss the ideas of CUDA threads and CUDA blocks, so we should be able to provide information how we want those blocks to look like. And this we will do with this kind of special argument. Okay, now I have prepared some examples that we can work on and become familiar with with CUDA. So I have created a repository on GitHub. So this is a repository. I have it here. I can put it on the chat. Just a moment. Why it's so big? Anyway, can you see it in the chat? Hello?
Yes, yes.
Yeah.
Okay, so when you are now on Cyclone, you can use Git to clone this repository. So if you can see my script, you get Git clone as I put it, and this will copy this repository. I have it open, so you should all be able to access it. So can you try and let me know?
Yeah, it copies and it's everything all right.
Okay, now I will go to my, so it should, what name I call it? So if you do ls, how it's called? Train event.
It's train CUDA.
Yeah, train CUDA, sorry. Yeah, so now you can execute the command cd and the name of the directory, in your case will be train CUDA. So you can enter this directory with the examples. So it was successful up to now?
Yes.
Yeah. Just a quick question as well. Before, when you were showing your modules that you're loaded in, you almost have 25. Should we load them in, or are we gonna need specific ones later on? That
I will discuss this now, Rafael.
Okay.
Discuss this now. Okay, so now you can enter this directory.
Yeah.
Okay. And there you can see several photos that are the exercises that we will discuss later. And there is one script here that if you want to see what is inside, you can do more, you can do less. Okay, and you can see what is inside. Okay, so inside you can see that I have first of all, this export is for later. It will allow you to use the Python in order to learn the next example. But for now, we will need to load those modules. So you can do it one by one. You can copy and paste them, or you can execute the script. And the script, actually what it does, it loads the necessary module for you, okay? And it compiles all the examples that we will work on now. So you know how to execute a script. So here is the script. You just do / and the name of the script, okay? And then you execute it, and this will compile. It will inform you which one it has compiled.
There are some troubles compiling exercise 5.
The warning, you mean?
Yeah.
Okay, this is a warning. It's not an error.
Okay.
So we do not worry about that. No.
Okay.
Okay. So, okay. Now I will start with the first example. So the first example, you can go to example 0, EX0. Okay. And in this example, you can see what it is in this example. If you haven't used before editors like the one usually used for non-graphical windows, we have what is called Vim. Emacs, I don't know if you have, but the Vim is already there. So if you write Vim and the name of the file, so in this case is this one, ex0_1.cu, okay, you can see inside the file. So do you see inside the file?
Yes.
Okay, so let me explain to you what it is. So you know we have the main function in C that we will call the very beginning. And now what is the goal of this small example is to find out what are the properties of the GPUs that we have. Okay, so one thing that one may need to find out is how many GPUs we have. So one way to do it is with the NVIDIA /SMI that I discussed before. And the other one is directed to write a small piece of code, and through the CUDA API, we can execute some functions, and we can figure this out. Okay, for instance, here I declare a variable n devices, and then I call the API CUDA command, CUDA get device count, and it will fill in this variable and devices how many devices I have. Okay, and after I have figured out how many devices I have, I can do a for loop on each device and find its properties. I mean, in the specific case of the Cyclone, we have each of the so the GPUs are all the same, but there are cases that a computer may have different GPUs. So you want to know how different are for each device. Okay, then there is a special structure, CUDA device probe is called. Okay, we declare it, and then we get the properties. So we pass the probe, which gets the properties, and then this structure is filled in with the properties, and then we can print properties of the devices. For instance, the identification number for each device, the name, and the global memory. Okay, so now I quit. So do you know how to quit Vim, or I tell you? So it is escape, and then colon and Q, and then enter. Okay, and then we exit the file. Now, if you have compiled all, as I said before, to run this compile command, you will see an executable that has been produced. This that ends with .x. And now we can execute it. So in my case, I execute it, it does nothing. So what it does for the rest? Hello?
Are we executing the .cu or the .x file?
The .x file, which is executable. The .cu is the source code that we compile. So you cannot execute your source code, right? So you have to convert it to an executable. So you do / and the name of the executable, like I did.
Yeah, it doesn't work for me for the executable.
And what it says?
Just nothing.
Yeah, this is how it should be, because you are on the front end and you cannot find GPUs. And in order to be able to do that, we need to allocate the node as before. Okay? So I will do this salloc that I said before. And it gives me a node, a GPU node. Okay. So you see now I'm on GPU 05. Okay. So yes, have also other data are on it. And then you can execute it. And it takes a couple of seconds. And you can see now it prints. And it says the device with number 0, its name is Tesla V100. It's the Volt architecture. It has 32 gigabytes. And then I print with the properties that I sent. I show you here in the code what is the total global memory. It says 31, which I have converted to gigabyte. But this 31 is because it's not 32 because some of it is used for some error correction, some other things. Okay, and there are more here if you want to see properties of the device. You can find out what is the shared memory you have available per block, or what is the warp size, the maximum number of threads, what we discussed before. Okay, so you can print all these properties from the device. So you were able to run this, those that they got access to.
Yeah.
Yeah, for me.
Okay. Okay, good. And okay, let's proceed to more interesting examples. Okay, so the other example is the standard hello world. Okay, so this example, it's just a printf statement, hello world. And this is a standard C code. There is nothing related to a GPU, right? So if we go to the example 1, okay, so you see what I did. We were in example 0, and then I can go one back with double dots, EX1. Okay, and now I go to the second example. Now,
I just ask, because I
yes?
just gained access. How do I get access to the backend of GPU 5?
It's in the chat. If you go
Okay.
and read up, where is it? Let me put it again. Yes, it's this one. Okay, I have put it again in the chat.
Okay, thank you.
Okay, so it has the 8 to give you now. So let me know if you cannot access it. Okay, so now I have in this ex1 underscore 1 what I show you in the example on the slides. Okay, and you can see it is this example. Now, if you try to compile this one with the NVCC compiler, by the way, the NVCC compiler is executed for each one. If you open the compiler.sh, you can see that it calls the NVCC compiler for each file. So you don't need to do it manually. I prepare here the script, and you are able to compile them all. But behind the scene, it executes this command, NVCC. Okay, you specify the architecture, which has to do with the compute capability that I said before. So for the Volta, it's 7. For the Ampere is 8. We have Volta, so we have this 7.0. This is the optimization level. I have put it to 3, the maximum one. The source code and the executable one that it will create. Okay, so this is what it will do, and this will compile without a problem. So if you copy and paste and execute this one, it will compile it in an instant. Okay, so actually here, as I said, the NVIDIA compiler takes this piece of code, give it to the host compiler, which can be a GNU compiler or something else, and it does the compilation. So if you execute it, we said we execute it by / and the name of the executable that we have created. It says hello world. So this works now, Christopher?
Yes, I'm in the backend now. I'm just trying to see how to get the source code.
Ah, yeah, okay. Are you having the train CUDA folder?
Sorry?
You have the train CUDA folder.
No, is it the one on GitHub?
Yeah, you have to clone it.
I'll get it.
Yeah, do git clone, and then you will have the folder. And then when you enter inside that folder, write the script compile all, like this, what I show, just like compile all, and we will compile all the examples that we will follow. Okay, and now we are in the example 1. Okay, now let's go to the next one. So let's make it more interesting. Now we will put a CUDA kernel inside, and we will try to execute it. So the CUDA kernel is like this. We said that the CUDA kernels that are called from the host and execute on the device will need the keyword __ global __. This is what you see here. Okay, and inside I'm doing a print of hello world. So this is a very simple example. And now I need the host, my CPU, to tell to the GPU, do the hello world. Okay, and now we will need this special kind of syntax. You see there are triple arrows right. And inside you can see 2 arguments that for now are set to 1 and 1, are related to how many number of blocks you want to specify and how many threads per block. Okay, now this example is in the ex1_2.cu. Okay, so this is how it looks like. It is as it was here on the slide. Okay, so try to execute it. // and then ex1 2.x. Okay, if you execute it, what is going on? Can you execute also the rest? Yes, no? I mean, I want you to see what is doing.
Okay, I just compiled everything. What are we doing?
We are in the folder ex1. So change to this directory.
Okay.
And then we are try to execute the example1_2.
Okay.
Okay, so please try to execute it.
It executed, though I suppose I didn't see any output because
you didn't see any output because there is a reason.
Yeah.
That I will like to explain now. But do the rest see this issue?
Yes, yes.
Yeah.
Okay. And the reason for that is that when the host calls this kernel, it does not wait for the GPU to wait the execution in order to proceed. Okay, so it proceeds and it comes to return 0. Okay, and it stops, and so it finish the code. So it does not wait from the GPU to execute this code, and this is because the call to the GPU kernel is asynchronous. Asynchronous, it means that I do not wait for you to finish. I proceed. This is what the CPU is doing. So we need to tell now to the CPU, wait until the GPU finishes with what it's doing before you proceed, so you can see the output. So it should be like this. So one needs to add this API command that says couldn't device synchronize, which means that the host will synchronize with the device. Okay, so this keep in mind. The way that the host calls the kernel is asynchronous. Okay, it means that it does not wait proceed. So at some point you need to synchronize with the NGPU. Now, in order to see it working with the CUDA device synchronize, we go to the example1_3.cu. Okay, you can see that inside it has this API command, so that we are make sure that we synchronize. And now let's execute it. Okay, if we execute it now, we see the hello world. Okay, so now we know this issue, and we need to keep this in mind. Now,
so the synchronize command forces the host to wait for the device to finish doing whatever it's doing and then terminate.
Yeah, so it will wait until here. Okay, yeah. So all the previous commands on the device are completed, and then the host proceeds to the return and finish the code.
Okay.
And finish the yeah. Okay, so now we will make this example even more interesting. So before, as I said, when we call this CUDA kernel and we pass this argument, I put 1 and 1. Simple case, just one block, just one thread. Now, if we want to have different number of blocks and threads, then you can specify the numbers that you want here, the number of threads per block and the number of blocks. Okay, and because now this piece of code will go to run simultaneously on different stream multiprocessor, for instance, than different blocks. You need to have some kind of IDs that you can identify what thread you got or what blocks in order to access different data based on those IDs. Okay, so if we have 3 blocks and 2 threads per block, so in total we have 6 threads, right? 3 times 2. And each one needs to have an identification number, so we can identify it. So there are special kind of variables now that exist only inside CUDA kernels that they take during runtime values. Oh. Okay. So hi Rafael, we have you back.
Hey, sorry, my internet went out.
Okay. Yeah, and those runtime variables, they have thread index, so we get the index of the thread, and because those things can be up to 3 dimensions, they have an internal variable that we can enter with .x, .y, .z for the 3 directions. Okay, and we have also the index of the block, which block we are. And this also can have x, y, z. And we have also the block dim, which is related how many threads we have inside the block. And the green dim, which is the dimension of the grid, how many blocks we have in total. So those variables get values of runtime. As you can see, I have never declared them like the standard variable because those, as I said, runtime variables. Now, if we want to see this example, I have it in ex1_4.cu. So you can see these examples, 3 blocks, 2 threads, with the CUDA and device synchronized as we said, and we print the values that we discussed. So we need to know which thread we have and which block we have in order later to handle them appropriately. And now we can execute this example to see what we see. Okay, so as you can see here, I have one printf statement. So you see it here, 1. But as you can see, I got a reply from 6 threads. Because as I said, we have 3 blocks and 2 threads per block. And you can see here that it's responding with different numbers. So we have 3 blocks from 0 to 2. And one inside you can see thread 0, thread 1, thread 0, thread 1. And now let's try to rerun it. To see something. Now I do not get different. Okay, anyway, this here. Okay, excellent leading. I mean, in your case, is what I am trying now to reproduce is that the order can be different. And because the blocks can run in parallel and one can run faster than the other. So it is not guaranteed that the order that they print the blocks are always the same. Okay, so this is something to keep in mind. And this as I said, it's because the blocks are supposed to run in parallel, so we cannot guarantee which one will print first and which second. Okay, so this is what it shows this example. So, sorry, I went very fast. Okay, now let's go to more interesting examples. And the more interesting example is to do vector addition. Okay, so you know vector addition, it means you have two vectors, you sum them, and you save the result to another vector. And in this example that I will show you here, the vector will have 512 elements. Okay, so I start with some standard pointers. Pointers, it means that it points to somewhere on the memory. And I have also device pointer, the size of the vectors that I go in bytes. So you always specify the bytes when it comes to memory. So it's the size n of the vector times how much byte is each one of the elements. In this case, are integer. So it will be 512 times 4 because each integer is 4 bytes. Okay, and now we will need to allocate memory on the device. So the CUDA API provides special functions of how one can allocate memory on the device. So if you want to to allocate memory on the host, you just do malloc. Okay, in C. Now on the CUDA API, there is a function called CUDA malloc. The CUDA malloc takes a pointer to pointer, so it's double pointer. So this is why here I cast to double pointer void the address of my pointer. Okay, so you need this as a fair argument, and then the size in bytes. We allocated the three vectors on the device. Okay, and then I allocated first also on the host before I will be able to modify the values of the vectors only on the host. Okay, so we have the A and B, the two input. I use the standard malloc. Okay, and then I initialize them to whatever random values I want. I allocate also C. Okay, and then the next step, as we said, is that we need to transfer the information now from the host to the device. So we have these three vectors. The two are the input vectors. So we need to provide to copy this information. So we need to use now the API function CUDA memcopy. So the CUDA memcopy takes the following 4 arguments. First is the destination pointer. Okay. Then is the source pointer, the size that we copy in bytes, and then there is a flag that specifies the direction of the copy. So in this case, we want to copy from host to the device. So we have the flag CUDA memcopy host to device. Okay, and we do this for both input vectors. Okay, now this API function like CUDA malloc, CUDA memcopy are blocking. Blocking, it means the opposite that I said before of asynchronous. So it's like, let's say, synchronous, in the sense that the CPU will wait until the GPU finishes all previous operations. So this is guarantees that before we call the kernel here, the copy is completed. from the host to the device. Okay, and then we execute asynchronously the kernel with one block and n threads, for example. So here I have put that I need as many threads as the number of elements, because one thread should take care of one element of the vector. Okay, and then after we pass this, yes, there is a question.
Yes, what happens if we try to allocate more threads than are available?
When you say available, you mean more than the size of the vector or more than the limitations?
The limitation of the server.
So not server, the GPU, you mean?
Yes, GPU,
so
sorry.
the compiler will complain.
Okay.
Because there are these limitations that you need to respect. But in this case, we do not exceed this number. Okay? If we want to have bigger vectors, we need to use more blocks, not just one. Okay? If you want to have bigger ones. You overcome this issue. So come to what I was saying. Now we can asynchronously call the kernel, and then we do a CUDA copy to copy back the data. But this is a synchronous operation, and it should wait until all the previous ones are completed, the two processes. So actually, the copy will wait for the kernel to be completed before copying back data. And here you can see that I copied the data from the device pointer to my host pointer. So because this is destination, this is, sorry, the C is destination, the D_C is the source now. And the flag says device to host, which is the correct direction that we want. And then one can visualize the vector, and in the end, keep in mind that if you allocate memory, you need to deallocate it. And the memory allocated with CUDA malloc is a CUDA free. With standard malloc on the host, you need the standard free. Okay, so this is what I do here. So now let's see the code in action. So this should be the 4. Oh no, I think now I need to go to EX2. So we go to the other folder of the example that I have the vector addition, the one that is EX2. Okay. So there, if you see the content of the EX2_, it should be this one. So I will open it with Emacs. You open it with whatever editor you want. Okay. So this is how it looks like. So this is the kernel that I will explain now. Yes, it's this one. Okay. And the code I just explained in the slides. And in this case, I also print the values of the vector just to visualize it. And here, this is the random, the function that puts random integer numbers. Okay, this is not so important. What is more important is the kernel here. You see, this is the kernel that comes with the acronym in global, sorry, the keyword global. And you can see here, I do not have any for loop. So if you will have a standard CPU code, you will do a for loop and you run over all the elements and you add one by one. So here instead, because we create many threads simultaneously, 512, and each thread gets on runtime a unique index. This is the threading the .x that I talked before. They can work on different elements of that vector. Okay, so here I do not need a for loop, and it will be done in parallel. Okay, so do you have questions up to now for this example? Okay, no questions. Okay, now let's execute it, and then we will do a small break, maybe 5 minutes break. So let's execute it. Okay, so we execute the standard way, and this will print the addition of 2 random vectors. So you can see here the values add up to as they should be. Okay, so and this vector addition has been done in parallel. So is it okay? It works for you?
Yes.
Yes.
Okay, so I suggest that we take 5 minutes break. So we come back in 10 minutes after 4. Okay. So 5 minutes break.
Okay.
Hello. Hello all. I think we can continue now after this small break.
Hey, just a quick question before we continue.
Yes.
Before I disconnected completely, I've lost all the modules, and I forgot to write down the command, the shell command that runs all the modules and compiles everything.
Yeah, the command is it's here. The compile all. It's in your folder.
Ah, okay. Thank you very much.
Okay, you are welcome. Okay, now we proceed with the next example. We are okay. So the previous one that we show, we had one block and n threads. Okay, in the next example, the XE2, if we can see it, the difference now it is that we put n blocks and one thread. Okay, and now we do the addition like this. So instead of putting thread index, what is changed now is a block index. Okay, because the thread index will be always 0 because we have just one thread per block. So what we can change in order to do the vector addition is the block index. Okay. Now, if we execute the example 2_2, which is the case here that I show, it again does the addition. So what we have understood, it is that we have the freedom to choose blocks and threads. Okay, there are pros and cons, and I will say about it a bit later. Okay, so the more complicated case is that you have both blocks and threads. So you have this n blocks and m threads. Okay, now if we have this case, one may wonder how we can, from the block index and from the thread index, to get a unique index, okay, like we did before, in order to be able to access each thread and different element of that vector. Okay, and I show here an example to help you understand. Let's say that we have 8 threads per block, so counting from 0 to 7. Okay, and we have 4 blocks. So 0, 2, 3, the blocks. Now, if we want to get a unique index, in order to, let's say that we had a vector with 32 elements. In order to get a unique index, to work on this vector, we do this trick that is an effective two-dimensional thing to one-dimensional thing. So you see this is two-dimensional, capturing as a block index, and from that we can get a unique index. So it's M, which is the size of the block, which has 8 threads in the specific example, the index of each block plus the thread index. Okay, and here, for example, if we want to work on the 21st element, this is just the block index with index 2. This is what you see here, and I go to thread 5. Okay, so 2 times 8 plus 5 is 21. So, and this, of course, can be generalized if you have also blocks and threads that they have 2 or 3 dimension. I mean, this example is for 1-dimensional case. Okay, so in this case, we just do it like this. And this runtime variable, I discussed it before, block dim.x, it tells us the size of the block, okay, in the x direction. We get the unique index, and then we can do the addition. And the kernel, we call it like this, n blocks and m threads. Okay, now this is in the example 2_3.cu. So let's open it. You see it, what I just discussed, the kernel here, how it changed now. And now it changed also how I call the kernel. So I put, for example, 32 threads. Okay, and since I have 512 elements, 512 over 32 will create for me 16 blocks. Okay, and this will allow me to do the addition. Let's run it. ext2.x and runs the example. Okay. So have you been able to execute it?
Yes.
Okay.
Yes.
Excellent. Now let's go to the case that our vector size is not multiples of of the size of the block. Okay. So up to now I made it like this, but in practice, it's not divisible. Okay, so we need to be careful in the case that is not divisible. What we are doing with the additional threads that I might have. Okay, so the idea now is like this. So you create for the residual part that it remains of the elements that is not divisible, you create an additional block. Okay, so in this additional block that we will have as the last block, let's say that is for the remainder part, and it's the remainder because not all the threads in that block will be able to do calculation, because if it was exactly divisible, it will not have a remainder. Okay, so we should be careful in that block. We do not allow threads to access memory beyond the dimensions of the array. Okay, so we need to find a smart way to do it. And a smart way to do it like this. Okay, so let me explain to you. So M, as we said, is our block size, which is the same for all the blocks. And then here we will compute how many blocks we need. So if it is exactly divisible, then this integer operator is just becoming n over m. It does not have any difference because m minus 1 over m, if you do integer division, is 0. Okay, but if it's not, then it creates an additional block if it's not divisible. And this additional block, as I said, it needs information to not exceed the boundaries of our array. So we need to provide in the kernel to know what is the size of the vector. Okay, so I pass it. Sorry, I pass it here. Okay, you see this is my kernel, and then I'm careful here and make sure that my index does not become bigger than L or equal, because I'm counting for 0. Okay, and then I do my addition. So in this case, whatever is the size of n, even if it's not divisible, it should be okay. So if we open this example that I say there, you see here, I say that I have 1,000, let's say, elements and 32 threads per block, which is 1,000 does not divide 32, of course. Okay, so it should create a 30. It should create 31 plus 1 block, and this plus 1 will not have as workload as the rest. And okay, if you execute it, it will tell you the correct value of adding the two vectors. Okay, now we discussed that it is on the user to decide how to organize the number of threads and number of blocks. Okay, so let's see now what are the advantage and disadvantage of the choices that we did up to now. So one thing that you need to keep in mind is that, as I said, there is a maximum number of blocks that you can run simultaneously on a streaming multiprocessor. Okay, there are also limitations about how many threads you can run per block. So you need to keep a balance. Okay, so you don't want to put one thread per block, because if you execute, for instance, 60 blocks simultaneously on a streaming multiprocessor, you actually execute 60 threads, okay, that are not enough to keep busy this strong streaming multiprocessor. So in order to keep it busy, you need to run more blocks with more threads, okay, and since you have you cannot split a block to more than one streaming multiprocessor, you don't want to have just one block, because then the other streaming multiprocessor we are sitting there doing nothing, okay, which is something that you don't want to do. So you need to have more blocks so you can distribute them to different streaming multiprocessors to get advantage of all of them. Okay, so the best thing is that you have threads per block and blocks per thread. Okay, so the issue is that the cons that I'm saying here is that it increases complexity. Okay, now if you have more than one thread per block, you can take advantage of using the shared memory, which is very fast. I will discuss this a bit later. Okay, and of course, if you have more than 32 threads per block, which are the size of the warp scheduler can schedule accordingly, depending of if you have already available the data from the device memory or not, to say which warps are active and inactive to hide the latency for waiting for the data. Okay, and okay, and so this is things that we will discuss now about the threads need synchronization and blocks running completely in parallel. Okay, now I will go to another important example, that is the dot product. Okay, the dot product is that you have two vectors, okay, you do an element-wise multiplication, element by element multiplication. So you have another vector, let's say, and then you do a reduction of that vector. Is you just sum up all the elements of that of the output vector. Okay, so let's start with this example. We write a kernel. Okay, this is x is the one input vector, let's say y is the other input vector. Okay, and now I do the multiplication. In this example, I just have one block and many threads, so I use the thread index in this example. No for loop, it is not necessary. And now I stored the result of this multiplication in some variable called temp. Okay, so the question is that this temp, where is it located? Okay, because this, every thread has to do it. So can anybody tell me where is it located? Okay, yeah, it's a bit difficult.
Is it on
question.
the host?
Sorry?
Is it on the host? No.
It cannot be on the host because this is a GPU kernel, so it has to be somewhere in the in what we discussed before. It can be in the device memory, it can be in a shared memory, it can be in the registers. Okay.
Mm-hmm.
So in this case, this temp exists for each thread. Okay, because each thread will come and do this, it will come and execute this piece of kernel. Okay, and each thread has locally this variable temp. Locally, I mean it is different for each thread. Okay, and it's stored in the registers. Okay, so all the scalar variables are automatically stored on the registers. And this is scalar in this case. Okay, and yeah, of course, you need to be careful that the registers are limited, but are very, very fast. Okay, and this is locally stored in the sense that it has a different value for each thread. But now, if it has a different value for each thread, how we can do the reduction? How we can communicate the threads in order to be able to reduce the values of those vectors. So one option that you have is that you return this vector to the CPU and you reduce it on the CPU. But there are better ways. So you can reduce it in the GPU, use it what we call shared memory. So as we said, shared memory is shared between the threads inside the block. So now we have one block, and let's try to share this information and do the reduction. Okay. So in order to define now some shared memory to use, you need this keyword __ share __. Okay, so and then you specify statically an array with n elements. Okay, so this is the size of the block, and of course in this case it is the same as the size of the vector. Okay, and then after we have done the multiplication and we store it in the local value for each thread, now we need to make it available in the shared memory. So each thread will take the value from this temp variable and put it in the shared memory in a different location. Okay, and then you can specify one thread. In this case, one can put an if condition and say, okay, in the case that I am the thread with index 0, I will do a reduction. So here I do a for loop over the elements of the shared memory, and I reduce them. Okay? And then you can assign the value back to a pointer that points to the device memory. So we can copy it to the host later. Now, the issue here is that there is some problem, and I would like to hear if you can see the problem. Okay. It seems that we do not have any bright ideas what is going on. So,
Can I ask,
yes.
just to clarify, the first command, the shared float, that creates
Yes.
only one instance of that variable in the shared memory, right?
Yes, it's one instance of the shared memory inside a block.
Okay.
Yes, because it is shared. Okay, I think now I have the example so we can see it. But okay, let me discuss now a scenario to understand the issue here. So let's say that the thread 0 performs a multiplication, this multiplication, and save the value in the shared memory allocation 0. Okay, now since all the 32 threads are in the same warp and execute instructions simultaneously, we do not worry about them. But the one that has an index 32, which is in another warp, it can be late. It is allowed to be non-synchronized. And then the thread 0 can reach this point where it does a reduction on that element. Okay, that it's supposed to be assigned from the thread that it exists in the second warp, which has an index 32. Okay, but it is not guaranteed that the thread with index 32, it has stored the value of the multiplication here. It is not guaranteed. Okay, and if it is not guaranteed, it means that we can face what is called in programming race condition. Race condition, it means that the outcome may change depending which condition runs faster. This is why I call race. Okay, and this is what I said before. If we go now to see this example in the code, we need to change a folder. Now this is example number 3. So if you change to example number 3, okay, the one that it is implemented is this 3_1.cu. Okay, so this is what I just described. It does the reduction. And okay, let's try to execute it out of curiosity. Okay, so this gives a number, which is the reduction of the elements of the element-wise multiplication or dot product. Okay, so in this case, we get the correct result, but it is not always guaranteed to get it. It could be, if you run it several times, you will not get the same result. So the way to solve this problem is that you need what is called a synchronization barrier on the threads. Okay, and this is a simple modification to the code. So after we multiply and we assign the value to the shared memory, we want to make sure that all the threads do not proceed to do something more, okay, and wait for all the threads in a block to finalize this point. So this is a synchronization by one of the threads, defined like this, __ sync threads. And it means that I wait for all the threads to reach here before I proceed. So this guarantees that when the thread 0 comes here to do the for loop, all the values have been assigned in our shared memory. Okay, so is it clear? Is it clear this point? Because this is very important. It's something that people that do not have much experience with parallel programming might find it difficult. But if you do things in parallel, you need to be careful about this kind of pitfalls. Okay, so now this is implemented is x3.cu. And okay, it gives the same result as I said, because this this condition was not create any problem before. But in order to avoid any surprises of cases that it could happen, you need to synchronize the threads. Okay. Now, the example that I discussed before, it goes, as I said, one block and then threads. So one block and 1024 threads. And 1024 elements, of course. Now, I have the same number of elements now, but however, now I want to have more than one block. So let's take 2 blocks. Okay, which means that 512 threads in each case. Now, we have 2 threads that they have the index 0, that they will enter these if statements, right? Oh, one from each block. Now, we did follow the steps that we said before. We get these unique indexes. Now we have more than one block. And now we enter here. Okay, so now we have 2 threads that they did the reduction. So they end up with 2 numbers that they need to reduce even more. Okay, so you can say I reduce it here and I assign it on the device memory. And the issue is that we may have again a problem here. Okay, and this is a very interesting problem, and I want you to tell me, what do you think? What it could be the problem here? Okay, it might be a bit difficult, and it has the root in the one fact that is that the blocks, as I said, are run asynchronously. So since they run asynchronously, they try to access the device memory pointer R simultaneously, not simultaneously, at different times, sorry. They can find it on different stages. And I will give you here an example to understand what I mean. First, let's remember what is the update process on a computer. Okay, so we, in order to update a variable, then we need to read its value on a temporal location. On this temporal location, we update the value, and then we store the result back. Okay, so we have these 3 steps that need the computer to do. But this can give a race condition against scenario. So we have 2 blocks, as we said, block with index 0 and block with index 1. And let's take the time slice 0. Let's say on the time slice 0, we have the thread index 0, which exists in the block 0. That reads the value on a temporal location from R. And initially it's 0 because we want to do a reduction. Those should have an initial value to 0. And then at time step 1, let's say that I updated by value of 4. for example. It can be whatever. So it does 0 plus 4 equals 4. While at the same time, because the block 1 runs in parallel, it does the operation that, okay, I read from R what I find inside, it finds 0. Now time step 2, the block 0, it has finished the update, so it saves back the value. What it saves? 4. Okay, and now on the same time, the block 1 should try to update its own value. In this case, let's say it's 5. Okay, so this has already finished. Now in the time step 3, it does nothing because it has finished. But now the block 1 has one more task to do. It saves back the value. Okay, so it saves back, instead of 9, that it should be 4 plus 5, it says 5. So we will have this wrong value if such condition happens. But there is a possibility that it could happen. So in order to avoid such race condition problem, we need what we call atomic functions. So atomic functions guarantee that during this process I just described, there could be no interference between different threads that they can give to this kind of issue. Okay, so if one thread try to update and someone else comes, then it should wait. Okay, and this kind of atomic functions can read the operations that we want, read, modify, and write, both double and single precision. And this we can do it both on device, on shared memory. Okay, and now this line that I had previously in the code to do this reduction, we need to replace it with this atomic add. And let's see the example now that it shows it. Is this one? Okay, let's go to one which we fixed this range condition already. So it should be the example 4. Yes, so you see here it has the atomic add. So if we run this, it will make sure that we are free of the race condition. Okay, so again, we get the correct result, and we have more than one block per thread. And in principle, you can do more to get to fill the GPU. Okay, so let's move a step further. So before I explain how we can allocate memory on the shared memory. Okay, so I say just put the keyword shared, and this creates a shared memory between the threads. Okay, and I say, okay, I want n, which was the number of threads, which at that time was the same as the number of elements of the vector. Okay, and there, because this was statically allocated, it was non-compile time the value of n, the preprocessor just replaced this n with the value 1024. Okay, but there is an alternative. The alternative is that one can dynamically specify what is the size of this shared memory array. Okay, and instead of directly putting what is the number of elements that we want to put, we leave this empty. You see, no element, no specifying how many elements we want, and we use the keyword from external. External means that it will be determined somewhere externally, and the somewhere externally, it's a third argument in this triple arrow notation that I said before. So it's the number of blocks, number of threads, and the size of the shared memory per block in bytes. Okay, so it is m times the size of a float if it's a float. Okay, in our example that we are doing and dot product with floats. So if we go to 3_5 for this example, you can see here that this is extern, as I said, this is empty. And in this example, I just put 32 threads and make sure that it's divisible, as I said before. So before I said n plus m minus 1 over m, this is the same now. And we executed our example. Okay, and we have our result. Okay, this is different than before because now I have created different size of the vector. Okay, so this is a way to do a dynamical allocation of the shared memory. Okay, now we will do now more complicated things. So up to now we didn't measure how much time we want to do some calculation. So what we want to do now is to measure some sections in the code to see how fast it goes and do some comparison with CPUs. And I show here an example how we can do the timings about the GPU calculations. So the CUDA API provides what is called a CUDA event. Okay, in the CUDA event, we can do several things. In this case, we have this special variable defined in the CUDA API, and we declare two variables, a start variable and a stop variable. And then with this start and stop, then we start creating events. Okay, and so we need to call this CUDA event create on the start and stop. And then on these events, we can start putting timestamps. Okay, so we can put a record on this event. So I start to put a record on the start event. Okay, I will talk about later on what is this argument. And then I have a section in the code that I want to do the timing. It can be that I allocate memory with CUDA_malloc, CUDA_main_copy, I copy data, execute kernels, for instance, and I want to time this section of the code. Okay, when I finish the section that I want to time, I start my event, so my stop event. And so I put a stamp on the stop event. And then if you want, you can continue. I mean, this will go, this will proceed. It's not means that you need to wait. I mean, the host need to wait for this. Unless we say that we want to synchronize the GPU task with this stop event. So it will wait until these calculations are done, and we reach the point that we have put we have put our stamp about the stop event. Okay, so we have two stamps now. We have the start and the stop. Okay, and now we can measure the elapsed time between those two events. So we can call the API function that you give two events, and then it computes the time elapsed between these two events. And this is given in milliseconds with a resolution of microseconds. Okay, so the resolution is very, very good. And then you can destroy those events, for example. Okay, now I have prepared an example in the folder ex4. Okay, so we can have a look. So in this example, I add two vectors as we did before. So now they are a bit big. You see what is the size of the vectors that we will have now. it's about 100 million. Okay, and I follow the procedure that we discussed. We create the event, and then we malloc. We do our allocation. We copy data. We add the vectors. We copy them back, and then we compute the elapsed time. Okay, we can print, for instance, an element to make sure that we did correctly everything. Okay, and then we destroy the events with free memory. Okay, so let's see this executed. Okay, so the elapsed time is given in milliseconds, as I said. We say about 340 milliseconds, and it gives me what is the value of the last element in case that one was to check the value of the addition. So if you go and check with what we did before with the addition of the vectors, you can see that this is the correct value. Okay, now I have briefly said that we have this argument that I want to discuss later, and this will take us to the other concept in CUDA program, which is what we call CUDA streams. Okay, so on those streams, we can put tasks that we want to execute on the GPU. So imagine that you have a continuous stream and you put one task here, one task here, one task here. And actually you can run those streams asynchronously on the GPU. So now we want to show an example here where this can benefit us. Okay, so in the events that you can put, it could be copying, could be kernel launches, etc. So now the GPUs have a special property that is very useful for high precision, for high performance calculations. And this is that when the GPU is doing calculations, okay, on the same time, you are allowed to copy in data from the host to the device. So up to now, we have seen cases where we block the host and wait until you copy data from host to device or vice versa before proceed to do something else. Now, we would like to show that there is a case that you can do this asynchronously and get advantage of this feature of the GPU to accelerate calculation. Now, if we want to be able to do this asynchronous kind of copy, we need to do the allocation on the host, I mean the memory allocation on the host in a bit different way. So before I use the standard malloc function to allocate the memory on the host, now one needs to use what is called CUDA host alloc. So as the name says, CUDA will be responsible for the allocation that will happen on the host. Okay, and this kind of allocation is special in the sense that it's page locked. So when I say page locked, it means that when the host starts an application, it has a virtual memory. Okay, so the mapping, there is a mapping between the virtual memory and the exact physical memory. And this mapping is done in order to avoid have blank spaces in the memory allocated. Okay, and these pages that the virtual memory take care of it can be page log or pageable. Okay, and if they are pageable, it allows you to fill these gaps that they could appear if you allocated the allocated memory. But if it's page log, you can have gaps, so you can run out of memory easier. But they have the advantage that the GPU knows directly on the physical location of the CPU where it could hide the data. Okay, so in order to take advantage of this asynchronous copy, we have to do this CUDA host alloc, which makes the memory page log. Okay, and in this case, because we did it with CUDA host alloc, we need to free it with CUDA free host the memory instead of the free that I did before. Okay, and now let's see an example. So we did extensively the addition of the two vectors. Okay, and the way we did it is that we had to wait to copy the full size of the input vectors from the host to the device, and then start doing the execution. However, since we have this feature of overlapping computation with communication, we can take advantage of it. And let's see now how we can do it having two streams. Okay, so let's say that we have that I have the big vector, so and we break it in chunks. Okay, so let's take the example that I break it in 4 chunks. I can start copying, okay, in an asynchronous manner the first chunk, and then I call the kernel, and I do this in a synchronous manner, so I don't wait. And you put on another stream that I copy the second part of the vector, the second chunk of the vector, sorry, and then I call the kernel on that second chunk, and then of course you need to copy back the data after the calculation is completed. So if you put them on different stream, it means that they are allowed to overlap in the calculation. So within one stream, okay, you cannot overlap things. But if you have 2 streams that are executed asynchronously, it is possible that the call kernel to do the addition of the first chunk overlaps with copying the data to the GPU for the second chunk. Okay, so like this, we can hide the latency of wait copying and not doing anything on the calculation aspect. So did you go to this point? I mean, please tell me if it was not clear so I can repeat it how it works. So this means nobody got it or someone got it? Okay, so maybe I can show the example. Yes?
Somehow, if you can.
Yeah, I will try one more time, okay? And then I will show the example and hopefully it is not clear.
Thank you.
Okay, so now imagine that we have 2 streams, right? So on those streams, we can put a task to be executed. And the tasks that we put on the stream to be executed, within the stream, you cannot overlap them because they follow a flow in this stream. Now, if you create one more stream and you put task on the other stream, you are allowed to overlap task on those streams. And the GPUs are allowed to overlap moving data from the host to the device to the calculation. Okay? Now, the idea is that if we break the vector in chunks, let's say that we break it in 2. Okay, So we start and put that I want this task to be executed on the GPU, which is copy the data from host to the device on the first chunk of the vector. Okay? And then I put also as a task that I want my execute my kernel on the same stream, like I show here. Okay, now I put also in the other stream that I want to do the same thing, but on the second chunk. So this thing, you tell them, okay, you can be done asynchronously, so I do not block anything. So I let those streams to run on the same time on the GPU. And then there is a possibility that when the kernel on the first chunk of the data is executed for the addition, okay, the copying that has happened for the second chunk, I mean what I show here, the copy on the second chunk of the input data, to happen simultaneously. Okay, so this you use, you hide the latency of waiting data when you do the computation. And also when you want to copy back data. If you want to, when you finish the execution of the kernel of stream 0 or the first chunk of the vector, you need to copy it back, right? So the step when you join it, when you copy it back, you are allowed the kernel of the second chunk to be executed. So you can also overlap this piece of a task. And this really benefits of the feature that you are allowed to overlap computation and calculation of the GPUs. Okay, and now I want to go to an example and show you how we can really implement this idea. Okay. Now, in order to be able to do this, again, I have my host pointer. So you have two input vector and one output vector Z. So X and Y are input, and Z is the output. Okay, and we have stream 0, and we have stream 1 as I showed before. So for each stream, we need pointers to be able to put the copying of one chunk and the copy of the other chunk, so that we will be able to simultaneously put tasks on the streams that we create. Okay, and then I start my start and stop event, as I said before, in order to do the timings. And now I create two streams, two CUDA streams. Okay, so first I declare them and then I create them. Now I do my allocation of memory as before, and I need to specify them that this is chunk size. Okay, so the chunk size that I said before that we break the vector. In this case, we have a vector that is 100 times our chunk size, and this is the chunk size. Okay, so it is obvious that we will have 100 chunks. And yeah, we allocate the memory for X0, Z0, Y0 of the chunk size for both streams that we need. And in this case, you need to be very careful that, as I said, the allocation of the host should be done in a page locked manner. So we need to use the CUDA host alloc now API function, which has the same format this one, and we use the default kind of allocation that is the page lock way. So we can initialize whatever values we want in our vector, it doesn't matter. And now we will go to the most important piece of the example. So as I said before, we want to put the task to be executed on two different streams. And this is what I do here. I start with putting a task in an asynchronous manner, okay, on stream 0. Okay, so there is a CUDA-MEM copy. So all the cases that we have seen before of the CUDA-MEM copy have been happen in a blocking way, synchronous way. Okay, so the host wait until the copy is completed to proceed. But in order to be able to do the case that I talked before, we need to do it in an asynchronous way. And there is an API function that has this async, and this allows us to proceed and don't wait for the copy to finish. So, and the direction is host to device. And now we have an additional argument. So we can say that this CUDA-MEM copy asynchronous in which stream to be recorded. Okay, so this goes first on the stream. So first added, first executed. Okay, this is the idea. First in, first out. And we we copy also the Y, and then we execute the kernel. So this is as I said it here. And then all this is done in an asynchronous way. And of course, we need to also put another task in our stream that we want after the execution of the kernel to copy back the data, all in an asynchronous manner in stream 0. So now we do not wait, of course, because every operation that I talk up to now are asynchronous. So we proceed and we say what task we want to put on stream 1. So we put a copy again asynchronously, but now we copy the next junk. So you remember before I say junk 1 and junk 2. Okay, so in order to go to junk 2, we need to step junk elements. So this is what it does here. It has I that identifies which of these 100 we will do, and then it goes to the next piece of junk. So we will be able to do what I was describing here. And we do this for both X and Y. We add the vectors, and we put them now in stream 1, the kernel, and also for the case that I copied back. Now, I forgot to mention that now we need to specify also, for instance, how many blocks we need and how many threads. Okay, so in the specific case, it's 1024 in each case. So then junk size was 1024 times 1024. So it is obvious that we have 1024 blocks, and each one has 1024 threads. Okay, so this for loop will be done 50 times because for each one we have two junks to be taken care. So in total, we will be able to do our 100 junks. And then because all of these operations are asynchronously, we need to synchronize ourselves with the stream 0, stream 1. This is what these API functions do. So we will wait until all the tasks we have put on these streams to be finalized. Okay, and then we compute the time that elapsed, and then we can we destroy the events that we have created, and this is the procedure. Okay, so now the interesting thing is to see how this works. So in the example that I showed before, without the events, so the vector addition without event, it took, as we said, 330 milliseconds. So now, in the example 4_2, I have introduced the events. So if you go inside here in the code, I have done exactly as I said here in the presentation. So as you can see here, this is our main for loop that goes asynchronously. So let's try now to execute it and see what it will tell us. Okay, so now it tells us that it took, instead of 330 milliseconds, it took 88 milliseconds. So it did exactly the same job in the end, but it did it much faster. And this we achieved because we managed to use this feature of GPUs of overlapping computation with exchanging data between the host and the device. So this was something very important to have in mind when you tell us about high performance computing. So do you have questions about this, the ideas of overlapping these two important things, computation and communication? So please let me know if this was not clear. I can discuss it again. Okay. Since nobody raised an issue, then we can proceed to discuss other important aspects of CUDA programming. So one thing that I haven't explained up to now is that there are cases that we may get errors. Okay, so it is important to have a mechanism to treat those errors if an error is raised. So for example, the CUDA API function like the CUDA malloc, they can throw an error for some reasons that I will see. So you need to know if such an error raised, what are your next actions? Okay, for instance, in this case, I define a macro, CUDA save call, okay, that we can put it when we call our CUDA malloc to make sure that no malloc is failed, okay? Because for instance, if you try to allocate a lot of memory that exceeds the available memory of the GPU, something should happen, right? It will return you an error. So you will not be able to proceed with your calculation. Or even the CUDA memcopy can raise an error if our pointers are problematic. So let's go and see the example here. If we go to EX5 now, 1.cu, okay, this show a case. This is our main file, and we try to do a CUDA malloc, okay, on a size that it is 31 gigabytes. It's borderline what a GPU can handle or not. Okay, so let's try to execute this one and see if the CUDA save call that I said here, you can get the CUDA error that has been raised. Okay, so let's try to execute it. So it tells us now that in line 21 there was an issue. So let's go to see line 21. So it failed to copy it. So let's try to increase it to 22 because it was very big. So now I need to recompile. So I modify the code. So I need to recompile. So compile. Okay. And then let's try to execute it again. So you see now I try to increase my memory demands from 31 to 32 gigabytes, and it tells me the check that I put that I'm trying to do an illegal memory access. Okay, this is because I have problems with my memory allocations, and it cannot be completed. Okay, so like this, we can get errors from MPI functions. But we have cases that the kernel can have an error. And how we get it? I mean, in the case of the API function, they return something, they return an error. But the kernels do not return errors like the API functions. So in this case, we can define a macro that is check the error on the last kernel. Okay, and this is here. There is an API function. Could I get the last error? That it gets the last error raised, and it prints to you. But of course, we need to keep in mind that the CUDA kernels are asynchronous, which means that you can reach your checkpoint, but the kernel not be able to finish in order to raise an error. So in cases that one is doing debugging, you can have the case here that you call the CUDA device synchronize, the device with the host with the device, as we said, and it will catch any error. It will return error, this one, if there is an raised error from the kernel. Okay, so here I have in exe52.cu also the case of CUDA check error. Okay, this is defined here as I explained now in the slides. And now I have the case of adding vectors that I showed before. And here I do a stupid mistake. Let's say I try to access a memory beyond the size of the array that I have allocated. That usually gives you segmentation faults in the standard codes. But this one, if we put here, where is it? Yes, we execute the kernel, and then we call this CUDA check error. So the CUDA check error is up here. It will synchronize with device, get the error, and print it if there is any error. But since I intentionally created an illegal memory access here, it should give me an error. So this is just to demonstrate to you that you can get errors from the kernel. So now we execute the 5_2 example. Okay, and it gives us an error and tell us that an illegal memory access was encountered. So we know. Okay, if you do not do this check, you may proceed and you don't get the error. So the values in the array might be nonsense. Okay, I think this was helpful. I think now I can go to, this is another example of copying data of accessing data between the GPU and the CPU directly without need to do a CUDA mem copy. But since I do not have much time, I would like to proceed to the cases that we use GPUs with Python, because it's very popular now, Python. So more and more people want to see how one can use GPUs and do coding on GPUs using Python. Okay, so the CUDA API that we talked before, provided from the CUDA toolkit, it's in Python. There are wrappers that allow us to use this API function that can be written in C, C++ through Python. Okay, and the way to do that is using what is called PyCUDA. So the PyCUDA is a Pythonic way, as I said, to access this CUDA API. Okay, and if you use Python and you want to install it, you can install it using pip install PyCUDA. Okay, and it provides function like we did in the CUDA API in C, the CUDA memallocc is just memallocc, the CUDA memcopy. So in that case, we are putting flags to specify the direction of the copy. Then we do memallocc and the underscore, and we directly specify like this: host to device, device to host. Okay, but now it's good if we have, if we see an example to get it better. And the examples to see the Python scripts are in exe6. No, sorry, I skipped that, so it is in 7. Okay, so you see the scripts ending with .py. Now, could you please tell me if you write which Python, what it tells you? So what location is your Python interpreter?
User being Python.
Okay, could you please run again this compile all? Because this compile all, it should export the path to a different Python. So if you run this command, it will point to a Python where I have already installed the PyCUDA to avoid now retry to install it without a reason. So if you execute this and write which Python, what it does?
For me, it's still the same.
It's still the same.
Yeah.
Okay, if it's still the same, if you say, if you write this one, it should directly take you to use that Python interpreter. So you can access this. So you put just
actually I fixed it. It's okay.
Okay, so this Python now has already installed the PyCUDA. So if one goes like here and say import PyCUDA, it should import it. Okay. Okay, so I think now we can see the example. Okay, now it is the example 7. Okay. So from PyCUDA, you need to it has a PyCUDA driver to get the CUDA API. Okay, and I will discuss also now how you can get the compiler, because you need to compile a piece of code that will be kernels now. But let's do it in a nice Python way. Okay, let's say that we want to add 2 vectors, A and B in this case. So, and we have a NumPy, the numerical Python library. And with this case, we straightforwardly say that we need a random vector. So we say NumPy random, give me 512 random numbers. Okay. And then C is our output. It can be empty for now. And then, as you remember also from the C code that I said, we need to allocate some memory on the GPUs. So now in this case, from this CUDA framework that I have imported here, I can say .memalloc. So this will do for me a memory alloc on the GPU. And you only need to specify the bytes. So from NumPy objects, they have this variable .n bytes. Okay, and this allocates an object on the GPU. And then again from the CUDA API, we use memcopy. Now it is _h2d. We don't need the flag that we had in the C case. And we put the destination and the source only. So, and we do this for both A and B vectors. We allocate also the C on GPU. And then this comes the nice part that you can do now with Python and GPU. So you have a source code specified as a string. Okay, so you will need, however, from PyCUDA compiler to have the source module. So the source module, you can pass a string, your source code, like it could be in C. Okay, for instance, we had the add vector, we have 2 input pointers and 1 output, and we did our standard indexing, and we did the addition. Okay, now after we have specified our source code of the kernel as a string in this source module, this step here, mod, you see here I got mod as a return from the source module. I said .get function. So this behind the scenes compile it. Okay, so this behind the scenes compile it as we did with the NVCC compiler, and gives me a Python object that I can call and provide here my pointers that they come from CUDA malloc. And of course, I need to specify, as we did in the C code, how many threads I want. So this is block, it says how many threads you want in each direction, X, Y, Z. Again, I do it one dimension. And then I do the CUDA memcopy back now with this MPI. And one can, for instance, see if there is any difference. So here I just say A plus B, a standard NumPy addition of 2 vectors, and compare to the vector I get from adding it on the GPU. Okay, so now let's try to run it. Now we don't need to compile it as we did with the C codes. Now, if your Python points to the location that I told you, you can just write Python. Otherwise, you need to follow the full path that I just gave you in the chat. Okay, now if you write Python and then your script, it will execute the script on the GPU. So it says that the total difference is 0. It means that our result vector coming from adding it using NumPy functionality is the same as we did it on the GPU. So it means that we can really use Python and CUDA together. Now, let me go to make it easier. So the first example is to use the one-to-one correspondence, how you can do it on C and on in Python. Now, the PyCUDA provides some more flexibility if it has to do with the with arrays on GPUs. And here I want to show an example together with a matrix multiplication using a CumBLAS. So CumBLAS is like the BLAS functionality that one has in basic linear algebra. So addition of 2 vectors is standard in basic linear algebra. Multiplication of 2 vectors is basic linear algebra. So I will show in this example how we can do a mathematical multiplication of GPU using Complex, which is a library provided from NVIDIA about basic linear algebra. Okay, now we will go a step further, and from PyCUDA we will use GPU arrays. So the GPU arrays allow us to do something like this. Let's say that I have an NumPy array of these dimensions that in the end I will multiply into a mathematical multiplication. So they have elements 10,000 times 20,000, 20,000 times 10,000. So if you multiply them, you will get something 10,000 times 10,000. Okay. I will say later what this order equals f means. So, and then we want to put this on the GPU. We want to copy. So if you say GPU array dot to GPU, it takes this A that is on host on the CPU and put it on the device implicitly behind the scenes. And you get this object here. And now we can have an empty array for the our output. We get the dimension, okay, for each of the two matrices. And now we want to use CumBLAS. CumBLAS use the same convention as BLAS in the sense that the arrays are stored in what is called Fortran format. So the Fortran format is a column-wise way to put elements in the array. So it does column. So you have also the option to do it rows, the way that you put them. In this case, you say that I want it in the format standard here. This is what it means order equal f. Okay, so that I will be able to use the CumBLAS because this is the format that it needed. And in order to start using CumBLAS, I said it here. Okay, so we need to use some wrappers that are available for CumBLAS, and this provided by what is called Scikit-CUDA. Okay, which is what I'm doing here. And if one was to install it, I give here what is the way to install it. So pip install Scikit/CUDA. Okay, and this provides wrappers to CumBLAS, wrappers to QFFT. FFT means fast Fourier transform for those that they want to use Fourier transformations. And QSolver provides some solvers like LAPACK that one can compute eigenvector, for example. If you have a matrix, you can compute its eigenvector. But okay, in this example, we'll concentrate on CumBLAS. Okay, and okay, first, before you call CumBLAS, you need to create a handle. A handle means that you initiate the CumBLAS library. Because there is some overhead to initiate, you initiate once, and then you use it as many times as you want to do calculation. And here for CumBLAS, I call CumBLAS, this means D, double precision, G means general matrix multiplication. Okay, the arguments are standard, one can find it in CumBLAS documentation. What is the order for now are not so important. And this, it does the multiplication on GPUs. And then after you finish, you can destroy your handle. And then you can view your, so where I have, here it will put the data directly to the C, to the result array. Okay, and then you see that from now on I can view this in a format, in a Fortran format. So it interprets like this. Now, after we have done this on the GPU, And since we are doing tests, it's good if we test if this agrees with the multiplication, if I have done it using standard NumPy. So NumPy has a linear algebra that you can do dot of two matrices. It means you will do the multiplication. And I put some timers here. So I can measure the time, so we can know how much faster is on GPU or on CPUs. And by the way, NumPy here behind the scenes calls the BLAS functionality, which has been implemented in low level in Fortran. And it's multi-threading. In the sense it will run on all the cores, on the CPU cores that the node has. Okay, and then we see here if there is any difference between the two results. If there is, it means that we did something wrong. If there is not, it means everything is fine. And we see the times. Okay, now let's run it. So you can run it and see with your own eyes what is going on. Okay, this is a warning. It's not an important one. Okay, in GPU multiplication using cuBLAS, it says that it took very little. You see here 0.00045 seconds. And on the CPUs, it's about 2 seconds. So it's so many times faster on the GPU than on the CPU. And for computing the total difference, we know that they are exactly the same values. Okay, so with just this simple thing, using cuBLAS, we're able to accelerate so much multiplication. Questions up to now? I mean, have you tried to run it as I did here with Python?
I'm getting an error.
Yes.
It says it's an import error about the lib courant, I think.
Courant?
No, it's.
Can you post the error that you get?
Yes.
I mean, what about the rest? Have you managed to run it without error?
Maybe I forgot to do one of the commands previously.
Yeah, but the Python that you run is what I told you. I mean, which is the location of the Python that you are trying to run?
It's NVMe H Hajianago.
And you are on a GPU node?
Yes, GPU 8.
Interesting. Okay. It's not clear now what is the issue of libcudaran cannot open a share object file, not fetch file or directory. And you have the modules loaded, or? If you do module list, what do you see?
No modules loaded.
Yeah, okay. So I think the issue is that try to compile to load this module. So try to load this module.
Okay.
And try to rerun. So I suspect that because you didn't have loaded the CUDA toolkit, you may not be able to see the libcurrent.
Okay, I think it's running. There's a warning, but yeah.
Okay, yeah, this
yes,
warning is not a problem. So now it's running, and you can see how much faster you can do it on the GPU. I mean, especially the matrix multiplication is much more efficient on the GPU. And the reason for that is that it's a compute-intensive operation.
Yes.
Okay, the vector multiplication is memory. It has in the sense that you have the elements and you do just one operation with them.
Yeah.
But in the matrix, you have much more. So you reuse the data. You don't have to move much, but you need to compute a lot. Okay, very good. So I have more nice exercises that we can have a look. And now we want to do something. Hopefully, I think this is the last example because it will take some time to do what is called like a fractal. If you are have seen before fractals, if you can zoom in as much as you want, and you still see patterns and patterns emerging again and again. And this is motivated by some mathematical studies that you can use imaginary numbers, and you can reapply on those numbers again the same function, and you can get the bounded size, and you cannot diverge and get very big numbers. So what we would like to do now is to build this beautiful image here. And the pseudocode that will allow us to build this Mandelbrot sets, it's this simple one here. Okay, so I will go briefly through it. However, all the details are not very important for the example. Is that you want for each pixel, so here you can imagine that this is a picture, so it has a pixel. So for each pixel, you need to get a color. Okay, and this color, you can get it using this Mandelbrot set. So you can get your initial, let's say, location scale by your coordinate of the pixel. So in this case, this goes from -1 to 1 and -1 to 1 in this direction. Okay, and then we have our complex number, which has as an x, let's say, the real part, and as y, the imaginary part. Okay, and there is a for loop here or while loop that you say that the magnitude of this complex number does not exceed 4, and you may set a max number of iteration, and then this is simply a complex multiplication. So you do this z square thing. This is x times x if it's real minus imaginary, plus 2xy. Okay, and then you add your c. Your c just your initial pixel location here. Okay, and you apply this again and again. So you take the function of the function. So this is what it's doing here. And as soon as this condition is not fulfilled, you will quit. And from the number of iterations that you have you give it as this integer number and different color. Okay, so from this, for each pixel, we can find a different color and draw such nice pictures. Now, since this can be done in parallel for each pixel, we can really get a big advantage of a GPU. So this is, again, to give you the idea, if parallelism is allowed in your code, how much advantage you can take of it. Okay, but I want to also go and show you how we can do this with standard Python I think this is easy for all of you to understand. And how we can use what is called NumPy that allow us to do a compilation of the fly of for loops in NumPy. And from that, we can build low-level codes that are more efficient. Okay, so it's like what Julia is doing behind the scenes, is doing an online compilation, sorry, and just-in-time compilation. Here you need to import what is called NumPy that you can. Sorry, here is pip install NumPy, not PyCode. Okay, and then there is also a part in NumPy that can do this just-in-time compilation for CUDA. But of course, there we need to rewrite some parts, and because we need to worry a bit about the threads and blocks that I have discussed before. But okay, let's go to this example that I have prepared. This is in the examples number 8. Okay, to see how this is implemented. Okay, now I import besides NumPy the PyLab. So the PyLab, it just allows us to do the visualization to create the images. And then this is the pseudocode. You can find it in Wikipedia. It's very easy, so we can see now the implementation of this thing now in Python. Okay, so it just takes the pixel that you want to work on. So the pixel, it has an X and Y location, and the max iterations that you want to do, as it was here, max iteration. Okay, but here is an input. And then I made it as a complex, as I say, the X represents the real and the Y the imaginary part. And then I start my for loop. I just do the Z square, as I said here in the pseudocode. Where is it? Oh no, in the slide I showed it before. We do this function. F to Z equals Z square plus Z. Okay, so this is what it does here. And it does it iteratively, in the sense that it will apply the function again and again. So the output will become an input to the next iteration. And if this is greater than 4, you can exit the for loop. So this is equivalent with this while loop with this condition. It's exactly the same. So this is a standard for loop in Python that we expect to be very slow. And now in order to create our fractal, we need to do a for loop over all our pixels. So this function is for just one pixel. Now we need to do a for loop over all our X and or our Y. Okay, here we can get what is our pixel size based on what is the margins that we put for our picture. Okay, and then for each number that is returned from this function up to which iteration it reached, we represent it as a color. Okay, so what it will create here is an image for every X and every Y, which is for every pixel, what color it will put. Okay, and now you create an image as a 2x2 array. In this case, I put this, let's say, size 1024 times 1536. And those are just integer. And then I create my fractal. So I take my margins, as I said, from -2 to 1 and -1 to 1. And then max iteration 20. This is not so important. And then that's it. We created the image and we save it. Okay, image 1. Now we would like now to see in Python how we can use just-in-time compilation. So we have for loops that are very slow, so we may use NumPy to do. So from NumPy we use JIT, which means just-in-time compilation, and JIT in order to do a parallel for loops, and this p-range will allow us to do p-range. Okay, now this part I put the decorator. This is how I call in Python. That this I want to JITify. Okay, and then here when I create my fractal, I say that I want an JITify, which means I want a parallel also for loop, which means that I want to use all the CPU cores. I enable it to be true, and here I say p-range. So you will do in parallel the x range of my figure. So as you can see here, I don't need to do significant modification. It's just behind the scene, the NumPy will take this for loop and convert them to low-level code for you. Okay, so this is the same. It's just I did these small modifications. And in this case, because it will be much faster, when I did it, it was very, very slow. I made it 100 times smaller, the pixels at the resolution that I did. So now I go and have 1 0 here and 1 0 here bigger, the pixel that I have. So I make it 100 times, let's say, more computational intensive. Okay, and then these steps are this. I forgot to tell you, the first time that you call it, then just-in-time compilation has overhead because it has to compile it. Okay, so the first time I call it, I do not do any timing because it will involve compile time. And then I call it again, and since it's doing caching what it has compiled, it will not have this overhead. So I time here the time I need to create the fractal using the JIT, the just-in-time compilation. Okay, and I can create an image again. But now it comes the more difficult part. So that I want to do this JIT, but using CUDA. So from NumPy, we can import CUDA. Okay, and now from CUDA that I have imported here, I can call JIT, just-in-time compilation. And the Mandel function that I have defined here, okay, now it will be compiled for device. Device equals true, so it will become a device function. Okay, and of course now we will need to have our kernel. So this is decorated by CUDA.JIT, the Mandel kernel. Okay, and as we know, when we have to do with the CUDA kernels, we have to worry about the threads and the blocks. Okay, so all we have learned about these runtime variables about block dim, grid dim, thread index, and this kind of things, we need to take it also into account here. So you say that you see that it can get a unique grid X, a unique grid Y, okay, in order to work on for different threads, blocks, etc. And now, when we are doing the for loop here over our pixels, we have broke it already to blocks and threads. So our X now will run in the specific domain that a block and thread will work on. Okay, so we do not have for loops that run from the whole range of the pixel. Okay, and this is the modifications that we need to do. How we break here the range to be different based on what is my index of the block and get where is the start and in X and Y. By the way, here is a 2D blocks. Okay, and this is done because it's more convenient if you have to do with 2D images. Again, I have my image here, the GPU. I say my block size, I make it 2-dimensional. Okay, and my grid also 2-dimensional. This is an option to take. And then I say my image, it becomes a device image. So you can say to device. And then this is the kernel. You can execute it. So instead of being these 3 ball arrows that we have learned in C, now you can put them here as in square brackets, square parentheses, and then the same arguments, and then you can copy this image back when it's done on the GPU. Okay, so this I have done again. I do not time it because this will involve the compilation behind the scenes, which is not fair to time. And because if you compile it, then you can reuse it as many times as you want. And then here I do the same thing. I just do the timing. And then that's it. Very simple thing now. We do it on the GPU in Python for those that they don't want to mess up with C codes. So let's now do our experiments, Python, run it. So this gives you the time that it took to create this Mandelbrot picture. By the way, I remind you that this case is on the CPU with no improvement. The standard for loops with Python. This case is again CPU, but with just-in-time compilation. So we compile the functions that are, and these two are 100 more expensive than the first one, because I put one more 0 in the X and one more 0 in Y dimension of the pixel. And as you can see how much faster they are, those two compared to this case, even if they are 100 times more expensive. And you can see here the GPU, how much faster it's in compared to the CPU. So have you managed to run it? Hello?
Not yet.
So what is still running?
No, I'm just going to the folder.
Okay, go to the folder and try to run it. So now I'm trying to copy the images so we can see them. So you can do an SCP to copy them.
I ran it, it's okay.
Yeah.
Okay, let me see. PNG. Yeah. Okay, so let's open the images so we can see them. How it looks like. So let's open one of them because all of them have done the same thing. Okay. So here you can see the images that we have created. It's a very interesting picture to create with such a small piece of code. And actually, there are many, many more ways to do fractals like this. Very nice mathematical things. Okay, so you did the run.
Yes,
so you confirm the findings.
Yeah.
Okay. Now I have more things, but it seems that we are running out of time, and I don't know if you are tired. I mean, the next thing that I have is to use distributed computing and Python and on GPUs. So for instance, you can have a multi-GPU thing in Python. So if you think you are tired, we can skip this one and finish. Otherwise, we may need half more hour. So whatever you want.
Would it be okay if we tried it home, especially if you provide us with the slides as well? And then if we have any questions about it, we can send them over.
The slides I cannot give it.
Okay.
But the examples, yes, you can. You have already the examples, and they are. Let me remind me if I write comments in the example. Okay, this is a simple one. Yeah, it's very short. It's not something so difficult to explain. So whatever you like. I mean, either we give half more hour or we finish. If you are interested, we can discuss it another time. Because here you today you had a full day of these sessions.
Personally, I think because it's very interesting, we should dedicate some more time another day so we can be more focused and not tired.
Okay. I mean, yeah, you are in the institute, so we can arrange again we can find some time to discuss it. By the way, you can run it if you want. The only thing that you need to be careful that you will need the MPI. But yeah, let's discuss it other time, because as far as I see, you are tired, and there is no point to extend it more if it's difficult to follow because you are tired. Okay, so do you have, I mean, maybe I conclude with what we have seen today. I mean, I couldn't finish everything, but at least to summarize closely what we have seen today. So we have shown in the beginning how we can write some CUDA kernels. So don't forget that we need this keyword global for CUDA kernels. For functions that are called from device and run on device, we need this keyword device. Now about the runtime variables, about indexing our threads and blocks. So these are very, very important. This notation to pass what is our block size, the number of blocks, the dynamical shared memory, and this kind of things. The API functions to allocate memory, to copy data, to free. We discussed how we can communicate using shared memory. We discussed the synchronization of threads, that is very important. We discuss examples about how to overlap communication and calculation that significantly improves the result. So we started to use Python and CUDA together. We have seen how we can use PyCUDA compiler, which behind the scenes use NVCC for the source codes that we provide. We have seen example how we can use basic linear algebra functions from